Hello, this is Project 2 for Physics 212, and we chose to do the buoyancy force topic. I'm Lucas Stassenville.
I'm Charles Carter.
I'm Jackie Whitler.
So the first step in approaching this problem is to apply our physics model to the topic, which in this case is in buoyancy, as this was the problem we chose. So the first step in applying this model is we're going to gather everything we can about the problem from the problem statement and any available material, including those found online or in the textbook that we can about said topic. The second step is to choose which facts, formulas, and laws are most applicable to the explanation of the topic, meaning formulas and other things that involve buoyancy or have variables that are going to prove useful to solving whatever problem comes up. And using these selected pieces, we can make a model and substitute different formulas and substitute in different models that will prove our point and allow us to reach a conclusion. In addition to this, afterwards, we are going to summarize the salient points of our explanation to make it more digestible and make it more understandable, and to make sure that we have some key takeaways that our viewers can see and make sure they can understand the problem in a way that lasts. Our current physics model includes forces, but does not include something important to understanding buoyancy, which is pressure. And our existing physics model includes free body diagrams, which can be helpful when solving problems involving the buoyant force. The way we solve this does mirror an explanation task problem in the physics homework, which is something to keep in mind for your understanding. So for the first step when describing the topic, as we do in an explanation task, is to look it up. What is the topic? And buoyancy is the upward force exerted by a liquid on an object submerged in said liquid. So in the diagram found at the right, you can see an example of that. The force exerted by the liquid at the top of a submerged object is less than the force exerted at the bottom of the object, and this is due to the depth of the object being submerged in more liquid. And the difference in these two forces is what causes a net force acting upwards, causing the object to float. Now, a note on the flotation of an object: if the object in the fluid has a greater density than fluid, then it will sink. If the object has a density less than the fluid, then it will float, which is why concrete, for example, tends to sink and things like wood tends to float.
All right, so here are some of the equations for some of the things that Charles just spoke about. We have a couple of equations that have to do with pressure. The first one is what he was describing with the pressure equals H times rho times G, where H is the depth of the object into the water, rho is the density of the water or whatever fluid you're using, and G is the force of gravity, or not the force of gravity, the gravity constant, or acceleration due to gravity. The second equation is the force from a pressure is equal to the pressure that we're talking about times the area that it's applying its pressure on. Yeah, the equation for water, or a constant for water density, is 1,000 kilograms per meter cubed. We're going to use gravity of 9.81 meters per second squared. And just a volume equation of a cube is volume equals a cubed, where a is a side length. Okay, so here we have a very cubical duck, rubber ducky, that's floating in some water, with the top of the cubical rubber ducky being just at the surface, where the pressure is zero, or the pressure is the atmospheric pressure, which we can call zero. And then the bottom of the rubber ducky is H below the water, and it has the pressure of the water pushing up on it. And this isn't a free body diagram, it's just a drawing of the pressure acting on it. And so we have these two equations up top here, that we went over on the last slide. And we can use these equations quite simply to find the force equation from buoyancy. So we start with our equation for the pressure from the water is the depth H times rho times G. We have the force, and then so we can get from that by substituting that into the other equation, the force due to buoyancy is equal to H times rho, the density, times G, the gravity, times A, the area at the bottom. And then you can combine together H times A, the height times the base of an object is just the volume of that object, at least for certain types of shapes like prisms. And then we can get the final equation, F equals V times rho times G. And that's all in the Y direction because the pressure is acting upwards on that bottom face. And this is equivalent to saying that the force due to buoyancy is equal to the weight of the fluid displaced, because it's the volume times the density times the gravity, which would describe the weight of that fluid. So using this equation, we can think about why some objects sink and some don't. So here is on the left here, we have an actual free body diagram, really simple one, just with the force of gravity pushing down on the cubical rubber ducky and the force of buoyancy pushing up on it. So we have our two equations. The force of buoyancy is the one we just found, the volume times the density of the fluid times gravity constant. And then force of gravity, we know is the mass times the gravity. And the mass can be described as the density of the object times the volume times the gravity. And so we know that an object is going to sink if the force of gravity is greater than the force of buoyancy, because then we have a net downwards force, and that means it's going to accelerate downwards, meaning it'll sink. So if we substitute in our two equations, we'll get the density of the object times the volume times the gravity times the density of the fluid times the volume of the gravity, and we can cancel out both the volumes and gravity on both sides and get that the density of the object is greater than the density of the fluid if we want it to sink.
Okay, so for our real world applications for buoyancy, there's several different things that buoyancy is commonly used in. For example, if you have a rubber duck that is sitting in water, it will float. This is because while there is just like regular air inside of the rubber duck, the rubber itself is lighter than air. And so it will cause the duck to float on the surface of the water. This is also a very similar thing to what happens with like fishing or trapping floats. They're usually made of rubber, plastic, or glass, and all three of those things, when filled with air, are lighter than the density of water, which allows them to sit and float on top of the water in order to see where your lure or trap is sitting inside of the water there. For ship anchors, we're actually looking at the opposite effect. We're wanting something to sink down, so we want something heavier than water. So a lot of times these are made of steel or iron or another metal like that, which has a much higher density than water, so it can easily fall through and sink to the bottom where it can be anchored. It would be kind of counterintuitive to have a ship anchor that floated on the surface of the water. It is also buoyancy is also something that people use in scuba diving, where you can see they add like sometimes it's necessary to add like weights into a vest in order to be heavy enough to sink in the water. And then also, if you're going deep enough, you have air vests, which you can inflate and deflate depending on if you want to rise in the water or sink in the water. So that's how you can kind of control your buoyancy for that. Looking at like applications in animals, fish also, their buoyancy is controlled by what's called like a swim bladder, which has fat in it, which is lighter. So the rest of them, it balances out so that they can actually like stay floating in the water. Whereas whales, an animal that needs to come up and get air, proportionally their lungs are smaller. And so as they dive down, it compresses, which means that there's less air, which means that they are heavier and they will sink to the bottom. Looking outside of water for buoyancy, we can look at balloons, for example, as I'm sure most of you, if not all of you, have seen. If you fill a balloon with helium, it will float due to the fact that helium is much lighter than air, and so it is it's kind of the opposite. It's like something floating on the surface of water, it floats in the air. Whereas if you just blew up a balloon with like regular air, it does sink because you now have the latex that the balloon is in into that equation. And so it is, in fact, heavier than the air around it, because the air inside and the air around it are the same density. So for our conclusion, some previous problems that we have looked at that could be similar to buoyancy are any force problems. So we haven't done any buoyancy problems directly in this class. We haven't done any pressure problems directly in this class. So that was very different to work with. However, we have worked with force problems. So we have worked with friction, and we have worked with like ropes pulling masses, which have different forces. And so because buoyancy is a force, it can be compared there. There is not a lot of comparison there, because it's a different type of force, because you have to take density and pressure into account. But it is still a force problem, and so we can compare it there. So overall, that was our problem for buoyancy. Thank you.